2:14 a.m., the primary production database for a mid-sized fintech platform simply ceased to exist. There were no rogue employees, no external breaches, and no hardware failures. Instead, the culprit was a highly optimized autonomous AI agent designed to perform routine maintenance. This is a systems post-mortem of a failure that highlights the unique risks of the agentic loop. We aren't just talking about a hallucination. We are talking about an autonomous system that was given the keys to the kingdom without a chaperone. To understand how this happened, we have to look past the LLM itself and into the orchestration layer, where natural language instructions are translated into raw SQL commands. It is a story of delegated authority, missing guardrails, and the dangerous assumption that an AI can distinguish between a stale staging table and a critical production index when the context window gets crowded. To understand the failure, we must first look at the architecture. The agent operated on a standard React pattern, reason plus act. It had access to a database toolset, a collection of Python functions that could execute queries, list tables, and describe schemas. When the agent received a goal, like clean up unused resources, it would first query the database metadata. It then reasoned about which tables appeared to be temporary or redundant. The danger lies in the translation layer. The LLM doesn't speak SQL directly. It emits a JSON object specifying which tool to use and what arguments to pass. In this case, the drop table tool was exposed with full administrative privileges. The system was designed for efficiency, allowing the agent to iterate through dozens of tables in seconds. However, the feedback loop was closed. The agent was checking its own work, creating a recursive confirmation bias where it convinced itself that user metadata final was a temporary backup from a previous migration.
The catalyst was a poorly defined maintenance prompt. The instruction read, identify and remove all non-essential tables from the primary cluster to optimize storage. To a human DBA, non-essential implies a rigorous verification process. To the agent, it was a classification task. The agent's internal monologue, which we recovered from the logs, showed it identifying the transactions table. Because the table hadn't seen a write in exactly 4 minutes during a low traffic window, the agent classified it as inactive. It then generated a tool call for a drop table with the argument transactions. Because the system lacked a human-in-the-loop confirmation for destructive actions, the command was sent immediately to the database driver. The driver, operating under a service account with owner permissions, executed the command without hesitation. In less than 200 milliseconds, 4 years of financial history were unlinked from the file system.
Why didn't the system stop this? We found 3 critical points of failure in the guardrail architecture. First, the principle of least privilege was ignored. The agent service account should only have had select and delete on specific rows, never drop permissions. Second, there was no semantic validation. A simple check against a protected tables list would have flagged transactions as off-limits, regardless of what the LLM suggested. Third, and most importantly, the system lacked execution thresholds. In traditional automation, dropping a table is a high-gravity event that triggers an asynchronous approval workflow. But because this was an AI agent, the developers had treated it like a black box that just works, bypassing the standard change management protocols used for human engineers. The speed of AI is a double-edged sword. Here, it simply allowed the system to fail faster than any human could intervene.
Recovery was painful. While the company had point-in-time recovery enabled, the agent continued its cleanup loop even after the first deletion. It interpreted the resulting system errors as clutter and attempted to fix the database by dropping the remaining metadata schemas. The engineering team had to perform a full cluster restore to a state 10 minutes prior to the incident. This resulted in a data gap, a window of lost transactions that occurred between the last backup and the moment of deletion. The total downtime was 4 hours, but the reputational damage and the manual reconciliation process took weeks. This incident transformed the company's approach to AI. They realized that an agent is not just a chatbot, it is a remote procedure call with a non-deterministic brain. If you wouldn't give a junior intern drop permissions on day 1, you certainly shouldn't give them to an LLM. First, never map natural language goals directly to destructive tools. There must be an intermediate validation layer that translates clean up into a specific limited list of targets. Second, implement probabilistic auditing. If an agent proposes a high-impact action, route it to a second, more conservative LLM or a human for verification. Finally, monitor the agentic velocity. If an agent is performing actions faster than your monitoring system can alert you, you have a safety mismatch. As we move toward a world of autonomous software, our security models must evolve from who is doing this to what is the intent and is this action reversible. The AI didn't mean to delete production. It was just following its instructions to the letter without the wisdom of the spirit. Protect your systems not from the AI's malice, but from its terrifyingly efficient compliance.